welcome Arthur Spirling today. Arthur is professor of politics and data science at NYU, where he's also the deputy director of the Center for Data Science. Arthur's research spreads across a pretty broad area of topics. Primarily, he's a program methodologist who also does work on comparative legislative behavior. His work has appeared in JASA, the American Political Science Review, the American Journal of Political Science, Journal of Politics, the Proceedings of the NLP, among many other places. Today, he'll be speaking on word embeddings, and please join me in welcoming Arthur.
Thanks, guys. Thank you very much. Can I just check with David that the sound is okay? It's good? Okay, thanks, David. All right, so thanks so much for having me today. I'm having a really great day here at Michigan. And I'm going to be talking about a project with a former student of mine, Pedro. Pedro is now a postdoc at Vandy in their data science institute there. And this project, in some ways, encapsulates a lot of what I'm trying to do at the moment in my career, which is think about these amazing and really interesting and deep developments in computer science and how we might use them in social science. So one of the conversations I was having with several colleagues this morning was, what happened to computational social science, right? Why isn't it a bigger deal in political science? And maybe one of the reasons is because we haven't thought carefully enough about how the lessons from CS can be transferred to political science. And that's one of the things I want to talk about today. So the particular thing I'm going to talk about is word embeddings. And if you know what they are, that's great. And if you don't, I'm going to give a very sort of quick summary of what they do and what they might enable us to do momentarily. And this is very much an applied paper because what we're trying to do in this paper is think about when we can use these techniques, when we can't, and really much more than that, a kind of workflow for thinking about how to assess their usefulness. So this is sort of a summary of what we do in this paper. We spent quite a lot of money and time running lots and lots of models and then having lots and lots of human validation tasks. And we hope it's a useful paper. So we hope that people will read our paper and they can use it in their own work to kind of motivate or justify why they've done things. Okay. As always with these things, the first $3,000 was because basically we're doing it incorrectly. But now we've fixed those problems. The comparisons are correct, as you'll see today. Okay. So let me start out with here's a deep learning problem. All right. So I want you to answer this question for me. All right. So I had to take a look at these portraits and answer me which one you think is more realistic. Okay. So which one of these has more realism? And it's up to you to define realistic. This is a crowdsourcing task, so I'm not really going to tell you what I mean by realistic. I'm just going to ask you which is more realistic. So who thinks this one is more realistic? Good. There's a hand straight up at the front. That's good. And who thinks this is more realistic? Very good. Okay, so the difference between these two gentlemen is that this is a real person, right? This is actually my boss. This is the president of NYU, okay? And this is an entirely fake image, right? So this was created in these adversarial network experiments where they're trying to, take pictures and create wholly new but ultimately fake humans. So this is something that was created by a machine, by a model, well, two models really, and this is something that is kind of real life. Right? And so there's a sense in which what you guys have just done is done a human validation task over something produced by a machine versus something produced by a human. Now, we're not going to ask people in this paper about images. We're instead going to ask them something like this. So I won't ask you your views here, but just think about yourselves doing this task where I ask you, here's a word, welfare, in whatever way you wish to think about that. And I ask you which of these words is a better context word. And I promise you I'll get into some detail about what the protocol was for this and how we went about it and the sequence of how we did this crowd task. But you would tell me which of those you think is more apt. And then I would compare the performance of the machine, the embedding model, with how other humans had done. But we'll return to that later in more detail. I think it's fair to say that if you're in this area, and my sense is that in data science, information school, and in the folks doing political methodology at least, right, people are very, very aware of word embeddings. They're something that comes from purported deep learning models, and we think that they capture something really important and interesting about language. So what are they? So if you don't know, they're essentially a real valued vector, and I'll actually show you a couple of them in a minute, or some splices of those vectors in a minute. And we generally think they can do two things very well. So the first thing that we think they're useful for and if you're approaching it from a CS perspective, no doubt you've already seen this, is that we think they tell us something useful for some downstream task. So maybe we're trying to predict what a customer might buy, and we know they've searched for a particular good, and through some word embedding, we can work out what other goods they're probably interested in because we know, how to represent that good in some space, and that tells us, what else we should advertise to somebody. By contrast, they are also intrinsically interesting. So if you come from a more linguistics perspective, and we're going to argue this is the sort of perspective to take today, they tell us something about what words mean in some intuitive and interesting way. They tell us something about the way that our politics is structured. They tell us something about the way that humans interact with other human beings. If you're going down this route, then you have to make decisions, right? You have to think about the modeling options that are available to you. So again, if you come from a CS perspective, you've already done this many times. You have to think about, should I represent this term document matrix in terms of TF-IDF? Should I do some other weighting of the raw counts, whatever it might be? And our central question today is this one. So how should political scientists choose among these extraordinarily complicated and involved models in terms of their very, very broad numbers of parameters that you might need to choose? So let me give you some background to this problem. And again, if you haven't seen word embeddings before, this is going to be on a little crash course. If you have seen word embeddings before, my apologies. It might be overly simplistic, but just bear with me. So for any linguists in the room, you're probably thinking, what does this guy from political science know about linguistics? Don't worry, here's a quote from Firth. This is the compulsory quote for all work on embeddings. You have to quote this or it's an insta-reject. So Firth was one of the people who laid out the distributional hypothesis. Others have done it, but he was one of the first. And in the 1950s, he has this kind of magical quote, which actually is quite hard to pin down. It was in this kind of weird edited volume. He says, "You shall know a word by the company it keeps." And the point of this quote is that if you want to understand what a word means, you have to look at where it appears in your language. So in English, you've got to look in English texts to see where this word appears with respect to other words. And you will, by doing that, you will learn something about what this word means to the humans who interact with this language. So here's an example that we give in the paper, right? So I want to learn something about coffee and tea as they relate to cup. I think they're somehow related, but I'm not really sure how. And so what I do is I produce an embedding, talk about that later, in this case in 2 dimensions. Now that would be a very small embedding by the standards that people use in CS, but just bear with me. So we've got an embedding in 2 dimensions. And as I said, it's a real valued vector, so we can put coffee in that space, that's just a point, tea and cup. And we observe this sentence in my corpus. I had a cup of coffee this morning. Or we observe, things like that. Here's my target word, coffee, so I want to understand what is the context of coffee, what can I learn about the word coffee? And around it, I draw a 2-word window. So we would call this a context window in CS, okay? But it's just a 2-word symmetric window, either side of that word. And what I learn is that, at least at very large scale, coffee and cup are often together in English. And intuitively, that makes sense. We know people talk about having a cup of coffee. They might ask for a cup of coffee. They might talk about coffee cups, or there was a coffee cup there. There might be a modifier on the word cup. But then I observe another sentence. I had a cup of tea this afternoon. Okay? So look, here's our target, here's our context, right? So we learn again that tea and cup seem to be similar. There appears to be something contextually related about tea and cup. But what I learned from that is that tea must be close to cup. But even though I never saw tea and coffee appear together, I learned that they must be similar in some sense, because they both have this similarity to cup. And you can imagine at large scale, this could be very interesting, right? We learn something about maybe, how liberals and conservatives think about the same issue in terms of what other issues they think it's near. And I'll give an example of that in a bit more detail in a minute. So what types of things are people doing in social science with deep learning? What are they doing with embeddings? So one thing that they're doing is they're trying to generate a dictionary. So a very common problem in political science is I want to do an information retrieval task. I have the entire congressional record, and I want all documents that pertain to a hot button issue in American politics like abortion. But I don't really know how to search for those. Just searching for the word abortion is confusing because maybe historically that's not how the word was used, right? So what I might want to do is generate a dictionary around the word abortion. And one way to do that is to look at the embeddings and the nearest neighbors for it. Maybe I want to model parliamentarians, right? So they're behaving in some way. I might want to think about ideologically what space they're in. I might want to improve the performance of some supervised learning problem. This is there's a very notable supervised problem in supervised solution, I guess I should say, in political science called README. And people are trying to use embeddings to improve its classification ability. Maybe I want to understand how words have changed in meaning over time. So even within our own lifetimes, a word like Republican has come to mean different things. That is to say, when I was a kid, Republican, during the Reagan era, connoted some sense of what that person might be politically interested in relative to what a Republican might be today. So maybe that term Republican has changed, and from a political science perspective, we want to understand how. So that might be a problem for embeddings too. So what's the problem? The problem that me and Pedro are interested in is how we make a choice between models, between architectures, between parameters, and in terms of our training set. So you will find lots and lots of models out there. So here a model is basically how do you want to construct these vectors? And the two big ones that we're going to talk about today are GloVe and Word2Vec. There are different versions of those models, and those are called architectures. There are lots of different parameters within those architectures, and we're going to talk about window size, which is how large a context you want, and how deep an embedding you want, right? So should I have a very, very long vector, or should I have a short vector? So you might be thinking, well, why would I not just want to have more information? Well, one reason might be computational time, but the other reason might be if you've ever looked at something like the principal components of, say, parliamentary voting or something like this, right? There's a sense in which if we fit 50 dimensions, right, we're overfitting. Right? On the other hand, if I fit just one dimension, maybe I'm underfitting. So I want to think about how long those embedding vectors should be. And then also, do I need to fit these embeddings to my local corpus, or can I use some pre-trained corpus? Can I just download information and use it? Okay, it would take me, you guys, if I set you the task of go and get me Word2Vec for Wikipedia in 2014, right, it would take you 5 minutes to download it. Okay? But that presupposes that pre-trained corpus at Wikipedia is what you want. Okay. So here's a controversial statement. All right. If you're in political science, it won't be controversial, but it might be controversial from a CS perspective. So we're going to assume, or we're going to make the statement that there are basically no downstream tasks in political science. Okay. So in particular, we're going to assume that although in principle there might be supervised tasks, it is not the case that those tasks are widely accepted. So actually, I'm curious, who here is coming in from political science or one of the domains? Okay, so if you're coming in from American politics, right, do you think that somebody who tells you that their dictionary or something worked for international relations, it will also work for American politics? That's a very skeptical, I would be very skeptical about that claim. It's very dubious, right? So we're going to say that there are in fact no downstream tasks, and so you can't use these kind of extrinsic evaluation criteria. So who's here from CS? Great, okay. So in CS you might say, okay, well we know what analogies are, because humans have put together these analogy banks. And so we can evaluate an embedding by looking at whether the analogies it comes up with match what human thinks are analogous concepts. So in general, we think that's not something that's possible in social science. Instead then, we're going to take a strong line and say that the only way that embeddings are useful and can be evaluated is, at least in this paper, is in terms of their intrinsic criteria. So basically, do embeddings give us political relationships that make sense? And to evaluate that, we're going to ask other human beings. The way we're going to do that is via something called a Turing test. Okay? So I think many, certainly the CS folks will know what a Turing test is, right? In the original Turing test, Turing proposed, it's a thought experiment in the original case, he said, well, why don't we think about human intelligence and human consciousness like this? We have a computer and a human, and they can output text in some way, and in particular they can converse with another human. So we send in a subject, we send in a human, and that human converses with a human and a computer. And the computer's task is to convince this human subject, that the other thing that they're interacting with is actually the machine, whereas the computer itself is human. Okay? This idea that we could deceive people and fool them into thinking that they were discussing something with a human, but actually they're discussing something with a machine. We're not going to do any deception today. Indeed, that would be human subjects research, which we're not doing in this paper. What we are going to try to do, though, is ask lots and lots of humans, crowd workers in particular, whether they prefer the output from a model, which for us will be a machine, right? Think of that as the machine in the Turing sense, or whether they prefer the output from another human being. Okay. So often in political science, and I think sociology, maybe to a lesser extent economics, right? We're skeptical about downloading things. We prefer to do them ourselves. And we're going to try and get exactly at whether this works in using this test. So one of the first results I'm going to report now, but I'll come back to later, we're going to get what we call human-like performance from embeddings. Okay? So in particular, humans, like you guys, when faced with a choice where one thing was produced by a model and one thing was produced by a human, about 50% of the time, at least for some of the comparisons we're going to do, you prefer the model output. Okay, that is saying that you prefer the embeddings version of what the context of a political term is to what other humans think it is. All right? So in that sense, it kind of these embeddings pass this particular version of the Turing test. But there's more than that, and one of the things I've done in other work is try to think about parameter choices. Because political science has so few of these extrinsic evaluation criteria, it makes it very hard for us to discuss in any sensible way what parameter choices somebody should make. So think about something like, in a topic model, how many topics should I fit? That turns out to be a somewhat fraught question because we don't have straightforward evaluation tasks. And the particular things that we're going to look at here are the window size and the embedding dimensions. We'll look at it in lots of different ways. And we're also going to look at the whether you should pre-train or do locally fit embeddings. So why would you do pre-trained? Well, they're very cheap. And as I said, if you Google now for Mikolov word2vec, you can download it in 5 minutes. Whereas locally fit, we have this idea that it's fitting our data better. I'll talk about some technical criteria to look at fit and stability, and then I'll do the Turing test later on. The good news, at least as if there's like one or two takeaways from this paper, is this robustness result here. So our position is that basically, unless you're doing something weird, like you have a very small corpus, or it's over a very long time period, and you're using very weird small windows, your choices that you make are pretty robust. So the inferences that you'll make from these embeddings are pretty similar. And I'll make that point in more detail later. And the other thing that we think is good news is that pre-trained embeddings work about as well as anything else. So if you're thinking to yourself, well, I have a domain of marketing, I have a domain of political science, I have a domain of economic reports or something like this, do I need to pre-train these embeddings? In our experience, at least for the texts that we're going to look at, and we're going to also look at more than, not merely English, we're going to look at other languages too, right? Pre-trained work is about as well as everything else. So if you take something away from this talk, it's that a pre-trained embedding will probably do fine for you. But let's get into how we're going to think about that. And then finally, we're going to talk particularly about these two extremely popular models, word2vec versus GloVe. Okay. So just a show of hands, who's heard of word2vec and GloVe before? Great. Okay. If you haven't, don't worry, I'll mention them. If you get into this space at all, it's the first thing people talk about is, which model should I use, which gives me better representations. So we'll talk about these. I mean, the main point that I want to make, and I'll make it sort of right at the end of the paper, is that there is some evidence in our cases that GloVe is considerably more robust than word2vec, although it's for specific reasons that I'll get into in a minute. But really, because we're doing intrinsic criteria, right, we find that they're both equally liked by humans. So for us, it doesn't really make a difference whether you use word2vec or GloVe, and claims that one is kind of intuitively better than the other, at least in terms of the words that it produces, we're very dubious about this, but we'll return to that in a minute. Okay, so how are we going to do this? We're going to train a series of local models, and we're going to focus on these two hyperparameters. So we've got the window size. Notice that this is doubled in some sense. So when I say a window size of 1, I'm talking about one word either side. And I guess this is a question for you guys, and I think sort of a rhetorical question is, what do we mean by context in political science, right? I think that's a sort of tricky issue. Do we mean a context as in a word that occurs very, very close to something, or a word that occurs within 48 words, right? I think that's kind of it's a tricky question in political science. And we'll talk about the embedding dimensions. So this is a very dense model. It's a tricky model, right? So it's going to be a lot of things to fit. And here we're talking about 50 dimensions. Again, if you know how these models work, then you know what we're talking about here. It's basically the length of that hidden layer. If you don't know what we're talking about, then just think about this as a bit like a factor analysis or principal components. We're trying to think, well, how many components should I fit to this problem? Do I want a very complicated model up here, or do I want a simple model that may be kind of overlaying several dimensions at once? And for each pair, we're going to estimate 10 sets of embeddings. And the reason we're going to do that is for stability, but we'll come back to that in a minute. And then finally, we'll compare Glove and Word-to-Vec. OK. So here are the evaluation criteria we're going to use. All right, I'm going to talk through each one. And this is the kind of primary contribution of the paper, but we'll talk through these as well. So the first thing I'm going to talk about is these what we call internal technical criteria. This might seem obvious, but you would be surprised. People often don't really talk about things like the model's internal performance, right? So if you think about something like how well it's fitting its local data, so something, the equivalent of something like an R-squared, right? So how well does this regression fit our data, right? There are similar ideas in word embeddings. So you've got this gradient descent problem, and you can record the loss. So we'll look at the model loss, and we'll talk about computation time. So one of the most common things that we hear from people who are thinking of getting into embeddings for social science is they say, I would like to fit one of these models, but they're just too expensive. I don't have all year to fit this model. We're going to have some very good news as far as that goes, and I'll get into that in a minute. We're going to talk about stability. So if you've come from the topic model literature, you know that non-convex optimization problems have this issue that we don't get the answer, the same answer twice in 2 runs. And the reason that's happening is because the problem is quite complicated under the hood. The same is true of these embedding models. You won't get exactly the same nearest neighbors each time. And so we want to look at some of this stability, and we're going to look across multiple initializations of the models to try and report how bad is this stability problem. So if I fit some model of a particular dimension, and then I tell you to fit the same model to my data, do we get the same results or not? And how far apart are our results? I'll talk about some rank correlations, which basically means how similar are the lessons you're learning from these models. And then finally, we'll compare them with what humans like. Okay. All right, so I'll give you a second just to have a look at our corpora. We're going to focus on that first one, the congressional record. But as you see, we've got some stuff that really varies in size, and varies in the period, and varies in the language. So one of the things that political scientists regularly deal with is kind of multiple languages. I wouldn't say Spanish and German are kind of low resource languages, but I think we don't really know much about how embeddings perform on them. But our lessons from the congressional record are going to basically carry over quite well to these other corpora, less so to the State of the Union, which is weird because it's long, but each document is quite short. So we're going to focus here. So just in terms of, I know from the CS perspective, this would be considered probably a small corpus, but I think that's about sort of medium size in terms of what political scientists are dealing with. 1 million documents or so is about right. Okay. So let's start with these technical criteria, right? What's going on here? Well, basically, as I fit within a given window size, as I fit more dimensions, I make my model more and more complicated, right? My model fits better, right? So this particular model loss is getting lower and lower, so it's just telling me the model fits better. In some sense, that isn't really surprising. And the interesting thing is what happens as we fit, larger and larger windows. So I don't think there's the kind of intuitive interpretation of this y-axis. We just want to notice that at window size 1, as I increase my embedding dimensions, I make the model more complicated, I'm fitting the data better. What about window 6? Okay, this is what you'll see in industry a lot. People will say, okay, let's use a context window of 6. All right, so it's an improvement over 1, although these aren't strictly comparable, right? But we see that it kind of asymptotes very quickly, right? And what about 12, and 24, and 48? Okay. So the point to be made here is that Pedro and I, like in the wild, when we're hearing about people talking about these models, they tell us things like, oh, well, these models up here that are very, very complicated fit much, much better than models with, say, 200 dimensions, right? So we're very skeptical about this, right? And even we're quite skeptical about claims that say, a 48 window model is going to be very misleading compared with, or is going to be much better than a 12 context window or something like that. The point I want to make here is that these are basically similar results. And that theme of saying, claims in the literature or claims that you read on Stack Overflow or something, that one model is better than another, we're very skeptical about. And this is the sort of beginning of that skepticism. There are some weirdly behaved models here. So in particular, a window size of 1 behaves quite strangely, but the rest basically looks similar. So what about computation time? I think this is less of an issue in CS. I know you guys do a lot of work on kind of optimizing how you're using various cores and all that sort of thing. But this is a common refrain in the political science literature or in the political science world. Somebody will say, I wanted to do an embedding and I just couldn't because it would take too much time. So let's give you some sense. So here we're talking about mean computation time. It's the mean because we do it multiple times, it's 10 times. So this is not unexpected. The fact that it's linear is not unexpected. But as I increase my number of my embedding dimensions, right, how long is it taking me? Well, a window size 1 is taking me about 25 minutes. Is that a long time? I don't know. I feel like if the conference is a year away, 25 minutes is probably okay. Now, if you're writing the paper the night before, that's not unknown in political science, by the way. And I know it's not unknown in CS as well. So what about window size of 6? Okay, so even now, right, this is not crazy in terms of computation time. Maybe it's taking you an hour and a half for a quite involved model here. 12, they're all linear, is what you'd expect. Okay, 24 and 48, right? So notice, and we're just really kind of getting started here, even for a very complicated model fitted to the congressional record, right, that the most complicated involved model you could do at 450 dimensions of this vector is maybe taking you 200 minutes, right? So maybe you're getting it done in 3 hours, something like that, right? Three and a bit hours, something like that. Okay. So again, please.
What machine are you training on?
Yeah. So I think Pedro was doing it on 8. Yeah. So we would expect. No, we weren't, and so we would expect some degradation in terms of like who's doing it on a laptop or something. That's a good question. So the question was, what was your actual machinery setup here, right? Because of course, these speeds are going to depend somewhat on how many cores you're using. So I think we were using 8 cores. We were trying to get a sense of what we thought an average political scientist would kind of have access to in terms of resources, and we think that's about right. Of course, this will be slower on a desktop, but given that the industry standard appears to be sort of fitting these types of models in here, which we get done in about an hour, right? You can imagine we're skeptical of claims that that you just simply don't have time to fit these. Okay, let me talk about stability and then the search correlations as well. So a general issue for us is that we think it's really hard to know how to compare 2 models. So one of the things that I promised that I would show you is what an embedding looks like. Okay, and I said it's a string of just real valued numbers. So here you go. So this would normally be of length 50. So here I'm looking at the embedding of the word welfare in the congressional record. We've capped it at 5, but this is what it looks like. Okay, we could estimate another model, 6300, and again, this would normally be of length 300. Right, it's just a real valued vector. And the question is, how can I compare those embeddings? Right, so obviously these vectors are of different length, so it's a bit tricky, right? I can't compare the output directly. So what we do instead is we say, okay, and this is a sort of common thing to do in social science, is to say, well, what I can do is compare the pairwise distances of the query that you care about, let's say welfare, with every other word in this vocabulary. Right, so these typically is very large, it's like 10,000 words, right? And then I can order the vector with respect to these 10,000 words. And that now is comparable because the size of the vocab is the same for every model. So now I'm just simply comparing vectors which are 5,000 long or 10,000 long. Okay? So that's the idea, and I can compare these vectors without too much trouble. The more tricky thing is what we want to compare in terms of inquiries. So the first thing that we did was try to write down politics terms. So these are the terms that we're going to kind of focus on in a minute. And we felt these were kind of interesting terms. Now I should be honest and say we tried a few different things, so some things don't work very well. So why do we pick these ones? So we've got these kind of what are considered sort of big issues in political philosophy, and then we've got kind of policy issues, and then we've got Republican and Democrat, right? So we wanted to ask people what they thought about the parties. So one question that you might reasonably ask is, why don't we ask about leaders? So why don't we ask about Clinton and Trump? Okay. So it turns out that if you ask about Clinton, the pre-trained models are going to give you very different outcomes to models that we would train today. So remember the pre-trained models, many of them are trained on like Wikipedia in 2014. So where Clinton means Bill Clinton, right? Not really Hillary Clinton. And Trump at that time was this kind of, it was a sort of small-time or big-time New York real estate developer, okay, not leader of the free world, okay? And so when the Wikipedia embeddings you're going to get, they won't really be recognizable to human coders. So there's a sense in which we picked words which we think will kind of work for us. And the other thing we did was we had a bunch of randomly chosen terms, right? Because a very reasonable concern is that we're kind of cherry picking the words that work, and maybe not all words work. So we had a bunch of randomly picked terms too. So if you haven't seen word embeddings before, I just want to give you a sense of what you get out. So here we're looking at this particular model, 150, and we're asking what are the words that are closest to welfare in this particular two-dimensional space. So, you know, reforming, comprehensive, Medicare, these were all close to welfare for this model. In a different model, reforming and child and dependency were very close and able-bodied, okay? So I just wanted to give you a sense of how, even though the term is the same, right, the model, the inference you're making from the model about what is the context of welfare in the United States, it differs between these models. And we want to somehow capture that. Okay, so let me talk about stability. So as I said, these are non-convex optimization problems. So as we fit these models, we have this problem that they're not stable. And that's actually a big deal in political science, right? The fact that you and I might get different results from the same model is actually a big problem. But I just wanted to give you a sense of how stable they are. So here we're comparing the outputs. And the essence of this is that we want it to be 1. So we want your version of the model that you're fitting to my data to be the same as my version. And when the correlation is 1, right, that means we're getting the exact same output. Okay? So let's start off with this 150 model. All right, and as we see, right, the worst it does is about 0.85. We put some confidence intervals on here. And the best it does is very, very close to 1. But as soon as we move to larger models, so as soon as we move to models which have a larger context, we're doing really well. Right, so claims about instability, at least for the congressional corpus, we're very skeptical about. I mean, that there is some instability. You're only getting a correlation of 0.95 between runs. But this is almost 1. And if we move up to 12, 24, 48, right, this is closing on 1. Okay, so when you're up here somewhere, you know, 300 dimensions, 6, 12, 24, 48, you're basically getting the same results every time. So we think some of this stability stuff might be a bit overblown. We're not saying it's unimportant. You should think about stability. But at least when we're looking at things like nearest neighbors, the stability is actually extraordinary, I mean, in terms of the congressional record. Okay, what about search query correlations? So far, the comparisons have been kind of boring. They're a bit dry. What we've been saying is, you know, on these technical criteria, like how long it takes to fit these models, or how correlated they are between runs, right? These models behave very similarly. But a much more interesting question is, do you get the same substantive results as I get if we run the same, if we run different models? So what we're doing in this heat map here is we're comparing, for our politics queries, essentially we're asking how similar are those vectors across 2 different models. So if you fit an embedding of 4850, and I fit an embedding of 150, how similar can we expect our results to be? Okay, and in this case, this is actually a pretty high correlation of 0.65. This is despite the fact that they're very, very different models. So just to give you a sense of some sort of highlights here, here's the kind of thing we're getting when we get to like 300, a vector length of 300, right? So we're talking about like 0.92 correlation. Okay, so claims that you should or should not fit kind of more complicated models, at least for these political science usage cases, we're very skeptical. These results appear to be basically the same. Okay, and again, we just sort of take from this sort of general robustness. We're skeptical of advice to the contrary. Even when the models are really different, like the window size is very different here, the model is, you know, is basically pretty correlated in terms of output. So finally, what about pre-trained versus locally fit? So again, I want to go over that difference for those who are not from CS and who are from social sciences. So when you have these embeddings, you have a choice. You can download the embeddings. It'll take you 5 minutes. It's ready to go now. So you want to know basically what are the nearest neighbors of this term. So I can download this Wikipedia embeddings. I can take a look. Take me 5 minutes. Alternatively, I can fit the embeddings to my sort of local corpus because I think that my corpus is so special and so important that it deserves its own embedding model. Okay. And we're asking the simple question, how true is that? Right? So if I used pre-trained rather than locally fit, how far off would I be? So we think of these results as being basically very encouraging. So here we're asking, if I compare the pre-trained 150 to the local 150, how similar are the results? And the worst it is a correlation of 0.5. But the correlation gets up to 0.7. All right? So basically up here we're saying, you know, even if you pre-train versus downloading in 5 minutes, you're still getting extremely similar results. Okay. All right. So thank you for staying with me on that. That's all kind of throat clearing because I wanted to sort of get through these technical criteria. We had heard this advice was out there that these things are important, and we think that that's basically false, or at least these things are a lot more robust than people give them credit for. But we haven't really said anything about the quality of embeddings per se. So far we've just said models run faster than you think, models are more highly correlated than you think, models are more robust than you think. But we haven't really talked about how we regard the output of those models. So what we're going to do next. So I'll give you a second to read this. This is what confronts you if you're doing one of our crowd tasks. They get the first quote too, so they're linguists too now. That helps them know that we're legitimate. And then we tell them this is the first task, so we're asking them to generate context words for us. So we say, specifically for a keyword, its context words include 2 types of words. So the first thing that we say is, and I'd be curious to hear your feedback on this. I mean, these crowd tasks have been done now. We're not going to redo them. So I'll certainly be polite in hearing your suggestions. But probably won't implement them, but that shouldn't put you off. I'll tell other people to implement them. So we say that they should occur in the vicinity of a keyword. So we sort of allow natural language understanding to people to interpret that, as in it should be physically proximate, basically. Or we tell them it could occur in a similar situation to the word. Okay? And then we give them examples, and we give them this tea and coffee example to try and help them understand what a context is. All right, and then we're going to ask them to generate context words for us. Okay. So here's what it looks like if you're in this first task. So we're going to have a first task and a second task, and the workers are going to be completely independent. So I'm curious, you guys can think about it in your own minds, right? If I told you to write down all the context words for welfare, what would you write? So notice here, this person has just started the task. They have to write 10, and they've written reform, help, poor. All right, now you just think about what you would write there, right? And that's going to be the human-generated list, basically. Okay, and then in the second task, and these are separate human beings, we're going to ask people to choose. We're going to give them a keyword, and we're going to ask them to choose their preferred context word. Okay? Just want you guys to think about what you would choose in this context. Someone says the word welfare, and you have to say whether the closest word is dependency or reform. All right. So in this particular case, the human who was choosing chose dependency, and it turned out that was a machine word. So this is kind of 1-0 to the machine. Okay. So the model has done well here and has actually beaten the human suggestion. Okay. Does that make sense for everyone? Okay. So very reasonably, you might ask, well, how are we doing? Right? So how much better can we do than humans? Do we do better than humans? So here, humans are the baseline. And for each prompt, each of our curated prompts, we're asking other humans to say whether they like the human or the machine better. And obviously they don't know which is which. So candidate here means what is the model that we're testing. When it's above the line, that means that we're beating the human baseline. So that means that the output from this model, in this case the locally trained 6300 glove model, is doing better than a human who's suggesting context words. Now this is a bit misleading because of course there are some sort of standard errors here, right? Some error bars, right? But the point to take away from this is that in this particular case, although it is generally true that humans prefer the output of other humans, it's quite close. right? So claims about, that humans are the gold standard relative to these embeddings was quite skeptical about, right? Especially when you bear in mind embeddings are really cheap, right? So certainly in these cases, these are so close that, they're almost indifferent between the machines and the humans. Okay, what about a pre-trained glove model? All right, so here, again, I want to kind of underline what's going on here and why we call it remarkable. So all that we have done is gone off and got the glove pre-trained, I think it's 6300 model, which you can download in 5 minutes. And then when we ask human coders, do you prefer the output from this model, or do you prefer what other humans who presumably are like you and have human language every day, they're basically indifferent, right? So on these prompts, they actually prefer the model output, right? So they prefer the output that comes from the point estimate anyway. They prefer the output that comes from the machine. On these prompts, they're basically indifferent once you take into account the relatively small sample size. And there are some in which they prefer what other humans produce. But this is pretty remarkable, given that this is essentially costless to produce, right? This is, whatever you think embeddings are for, right? We get tremendous success here. And there's nothing special about these comparisons. So the nicest feature of this kind of Turing test is that you compare any model with any model. In general, I would say that once you stop having humans in the mix, humans can't really tell the difference between these models. Okay. What about word-to-vec? So there's this kind of interesting debate that goes on, I think, in CS and in linguistics about whether word-to-vec or glove, whether one is better than another. And we're not really going to say one is better than another in this paper. We'll note first that obviously mathematically they're extremely similar. And so consequently, right, we expect them to produce similar embeddings. Our response to this is to say that actually this isn't the case. So it is the case that word-to-vec and glove embeddings look different. But it is nonetheless true that humans don't seem to notice. And I'll provide evidence of that. So the point that we're making is that it is true that glove and word-to-vec will give you different results. But it is also simultaneously true that humans don't seem to care, at least for these political corpora. Okay. So let's compare the glove pre-trained with the word-to-vec pre-trained. And the main point that you can see here is that, I don't think there's any kind of clear winner here. So every time it's above this line, glove is doing better. But, basically they always overlap. So who knows? Humans are pretty indifferent between them. Okay. And the question is, why is this, right? So sometimes the correlation is large and sometimes the correlation is small, which is surprising given that they're mathematically very similar models. So the main reason for this is that the way that we have discovered is the way that glove and word-to-vec treat rare terms. So just to be clear, this has always been well known, but what has not been well known is what effect this has in terms of the substantive inferences you make from the nearest neighbors. So glove tends to underweight these relatively rare terms, whereas word-to-vec underweights very high-frequency terms. And this has sort of some natural consequences, particularly in something like the congressional record, which I'll show you in a minute. So word-to-vec will find these very rare terms, which are basically typos, and sort of upweight them and say that they're nearest neighbors. So let me just give you a sense of this. So here are the nearest neighbors for freedom. Here are the nearest neighbors for glove, word-to-vec and glove. So if you guys just take a look at these, I think it would be fair to say that these lists don't differ very much, right? It's not like this list makes a lot of sense and this list is crazy or something. But the thing to point out is that word-to-vec tends to find a lot of typos and make them kind of highly ranked nearest neighbors. But once you kind of clean those out, right, humans certainly can't tell the difference between the lists. So they generate different results, but in terms of conceptually what the difference is it's very, very mild. I mean, to some extent, we would say we agree that glove is more stable in that sense. It doesn't find these weird typos and upweight them. But in terms of a simple treatment of just saying, I want these models to have the same vocabulary, humans can't tell the difference. So we're very skeptical that you want to use one. We don't want to give precise advice of using one over the other. We're not sure about that. Okay, so what have we found? And I want to sort of get into a more philosophical discussion. So we get what we call remarkable human-like performance. You can say it's not remarkable. I think it is in terms of how long we spend in political science training up folks to do dictionaries and things. we think that these models are pretty robust to the parameter choices. Now, we understand that the parameter choices that you're making in CS to optimize something very subtle are different to the ones that we're making. But nonetheless, we think that claims that you should use this model over that model, but we're very skeptical about those. If you're using 6300, it's probably fine. And furthermore, that these kind of default embeddings work really well. Right, so claims that you need to do local training, I mean, at least for these modern corpora that we were looking at, we're very skeptical about. Okay. And then finally, that glove appears more robust, but who cares? Because basically humans can't tell the difference. Okay. And really, if humans can't tell the difference, we're not sure in social science that we should care, basically. Okay. So some parting thoughts here. So one of the pushbacks we get on this paper is essentially that we're asking the wrong people. Right? So we set out in the paper to ask people who are essentially politically engaged in some sense. Right? These are political science questions, and so we want to ask people who are political in some sense. And what we use are crowd workers in a prime service, but nonetheless, and we do some screening, but nonetheless, right, these are in the end crowd workers. Okay? So basically it comes down to who cares what M-Turkers think. Right? That's a reasonable critique, I think. What I'll say is that if you've spent any time in political science in the last 5 years, you'll know that crowd workers are used a lot. People use them as research assistants, right? People don't believe anything until the crowd has coded it, basically. Okay? People talk about the big data revolution. What they're really talking about is how many crowd workers they can get to code things. But regardless of that, the contribution of the paper stands, at least in terms of the Turing test. Okay? So we're saying that in the end, if you want to find out if your model is good or not, you've got to find a way to compare what humans would produce versus what the model produces. So the second thing that people say is, look, this is just a wrong task. And they don't believe the results in which the model does better than the humans. And the specific reason they don't believe the results is because they say humans are really bad at producing lists. So when you were thinking about this exercise of what word would you say in response to the word welfare? What would be the nearest neighbors that you would list? Right? There's an argument that humans are bad at recalling this. Right? They're just not very good. So firstly, right, we think they did okay in these examples. None of the crowd workers suggest crazy stuff. They suggest things that kind of make sense. So we're skeptical about this kind of generic idea that they're bad at recall. But frankly, we're not clear that that's different to voters. Right? So my co-author on this paper, Pedro, in his dissertation research, one of the things that he worked on was essentially stream of consciousness representations by voters. So in psychology, what they do sometimes is they get a voter in and they say, write down everything that you can think of everything that you think of when I say the word Trump. And they write them down, and then they try to make an inference about this person's psychological state, right? Or how they relate to other people, how they relate to other Democrats, how they relate to other Republicans. So we think this is actually a standard task in other disciplines, and so we're skeptical of this critique. So the final critique we get is that basically, it goes like this, right? You cannot philosophically start out a paper by saying you have no downstream task in mind. Because if you really have no downstream task in mind, there's no point in doing the paper. All right? So you have to believe that the people are going to use these embeddings for something. Right? So you should say what that downstream task is, and then that will help people understand when they should use embeddings and when they shouldn't. And our response here is something like this, is to say, yeah, we actually agree with that philosophically. We don't have a downstream task in this specific paper, but we understand that everyone else has one. But we think this is as close as possible to ground truth. So basically, and I had this conversation at lunch, in CS, folks have a sense of what the ground truth is. The analogy bank is the ground truth, right? The state of the art in terms of precision and recall, that's the ground truth. Okay? We don't have that ground truth in political science, but we're trying to motivate it here. Right? We're trying to give that ground truth. Okay. So we're going to release all of these things, right? So this is my co-author Pedro. So we're going to apply these. You'll be able to get all the embeddings we fit, which took some time, although not that long. We have a GitHub where we describe the paper itself, and we've also written a kind of FAQ for this as well, which is sort of very chatty in nature, but it kind of guides you through what embeddings are about if you haven't seen them before, and how they might be used in political science and what we find. Okay. that's my last slide. So I'm very happy to take any questions. Thank you very much.
Questions?
Please.
So I thought you did a great job telling us why we might want to use some specification for index approach rather than another specification for index approach. I was wondering if you could talk a little bit about when you think it's appropriate to use a word index approach at all, say in comparison to more explicitly Bayesian and the topic approach.
Yeah, so that's an interesting question. So the question is basically, what we're trying to do is evaluate within this class of models what should you use, specifically for this domain of politics. But I agree, another and related question is, when should I use them at all, right? So what types of questions are they good for? They are already being used, right? So people have used them for kind of dictionaries already, and they seem to be excellent at generating dictionaries automatically. People have used them. I just saw some work from Jennifer Pan at Stanford, where she's using them in Mandarin to look at when certain events occur and when they don't. Because you want to sort of, that's a kind of information retrieval problem where you want to find events, and so you want to know what is close to this word in this space. So there's a sense in which I think they can be used anytime we want to understand something, what should I say, sort of deep about language. So one of the ways that they've been used as well in this sort of recent PA article is, as I said, to look at words over time. So a topic model is not going to really, well, you could push it a bit, but it's not going to tell you, what did the word Republican mean in 1950 versus what it meant in 2000, or at least that's not what topic models are designed to do, right? Embedding models are kind of designed to do that, because you can look at the nearest neighbors and get a sense, in a deep sense, of how this word has semantically changed. So I think if you care about the sort of deep semantics, and you care about how we use a particular word and how that word might differ between you and I in terms of our conception of the space of politics, I think embeddings are what you want. And of course, I mean, we're right at the start of using embeddings, so I'm sure there'll be lots of other applications. But I think if your problem is, I want to understand how people use words, then I think embeddings are kind of the way to do that. Yeah. Yuki, yeah. Yes.
Choosing between dependency and as appropriate for within the same context as whatever. It seems to me that whether which one is good depends on what. I mean, like as a political scientist, it seems to me that like those who have different political ideology
Yeah.
is going to give
Yeah.
different answers. Right?
Yeah.
So if you don't like welfare state,
Yep.
Is the same. It's in the same context as welfare. Whereas the other people might say, well, we need welfare reform.
Yeah. Yeah.
So I wonder sort of, if you could tell us a little more about how that constitutes.
Yeah. Yeah, no, that's a good question. So the question here is basically, so just repeat it, is basically, we know that the way that somebody thinks about a word is in some sense conditioned on their covariates. We can imagine that men and women think differently, we can imagine Republicans and Democrats think differently, so what should we do about that, basically? So firstly, I'm sure that's correct, that's number one. So number two is, if you start to take into account the covariate profiles of your human coders, then you're very close to human subjects research, and we want to keep it away from human subjects research. So when they're not the subjects of our experiment. So as soon as you're starting to do regressions or something like this, and you want to publish those regressions, you're now treating them as subjects, where you're giving them a treatment and you're seeing what their response is conditioned on the covariates, right? They are not our subjects, and they are simply coders for us, and we were very explicit at the start of the project, that's what we wanted to do. Third thing, though, is that in Pedro's own work, he's looked very explicitly at this, about how, whether Republicans and Democrats have different embeddings. And he finds exactly as you'd expect, that they have very different responses to these things, and they have different embeddings. Now, as a fourth point, what would be really good and really interesting is something I'm working on with Pedro and some other folks actually in this room, is how can we make that type of inference sharp? So how can we talk about the fact that your embeddings are statistically significantly different to mine? All right, so that's actually a complicated question because nothing in these vectors connotes a variance. So it's very hard to say that, oh, you have this statistical difference to me, right? And so we're trying to think about a regression approach for embeddings. But I absolutely agree with the critique, but we were very explicit about the way we did it precisely to avoid this human subjects problem. But it's correct, I'm sure it's correct, yeah.
Still time for one more question?
Yes, please, sir, yeah, go ahead.
So you said you use pre-trained models and locally trained models. Did you try training of pre-trained models on your data, like transfer?
No, we did. Okay, so you're saying you're asking about where do the pre-trained models come from, basically?
No, I'm saying, did you train your pre-trained model with the data again, like this transfer learning, right? You can train your word-to-word models with your data again, with your specific corpus.
Got it. Sorry. Yes, we did not do that. No, we didn't. So, pre-trained for us is just the download from the Wikipedia and GigaWord, and then the local is start. Yes, from scratch on the million corpus. You ask a good question though, which is that couldn't one do something in between? So we're sure that you could. I think in some sense we wanted to limit the total number of comparisons we're going to do in this paper, but that would be a good next stage for us, and I think that's a fine suggestion. Yeah. Thank you.
Any additional short questions? Okay, join me in thank you, Arthur.
Thank you very much, guys. Thank you.